This video introduces our work on social media crisis mapping, which has been performed as part of the TRIDEC project. Our work focuses on natural disasters, such as tsunami and tornado, and we aim to use Twitter as a type of social sensor, as it is both low cost and very fast at reporting incidents of this type. Our approach is to first download street map data for at-risk areas of interest, and then calculate baseline statistics for these regions to provide us with a background noise level. We then use natural language processing techniques to match location entities from our street data to tweets which are streamed in real time. The final result is a hotspot layer showing incidence reports which can be rendered using mapping software such as Google Earth. We now show our crisis mapping in action for the Hurricane Sandy flooding which occurred in October 2012. The data shown here is for a period of 5 days, and you can see our flood maps are updated in real time for the New York and Manhattan region. The light blue lines indicate reports of flooded streets, and the larger polygons indicate clusters of street flooding and building floods. The map presented here allows the user to browse affected areas, looking at Twitter reports, and zoom in on areas of high interest. In addition to roads and flooded areas, we also show points of interest such as subway tunnels and individual buildings. These can be zoomed in and clicked on to get a bit more information. If required, we can also pop up the text of the tweets themselves, allowing a user to see exactly what's being talked about when there's an incident report of flooding on a particular street or a particular building. In the video here we can see the user zooming in on the area of Wall Street because during the Hurricane Sandy a lot of Wall Street was flooded, along with the Battery Park area and the Holland Tunnel. For any given crisis mapping deployment, we can change the sample period and the time window over which samples are displayed, allowing users to configure the timeliness of the information which is shown on the map. We can also change a quality threshold, which determines the number of incident reports that are required before a feature appears on the map. This has the effect of increasing the precision of the results which are displayed to the user, and therefore reducing the number of false positives. Evaluations have now been published on both the geoparsing accuracy of our system and the usefulness of the maps themselves when compared to post-damage assessments performed by individual experts. For geoparsing accuracy, we ran our system on a benchmark dataset published by Carnegie Mellon University. Our geoparsing approach of using street map data has a similar F1 score but a much higher precision, making it more suitable to our use case where we want to minimise false positives. Our use of street map data also makes our approach relatively language neutral, allowing us to run across a number of different European languages. To validate this, we ran our system on a number of different events based in different countries, including earthquakes in Istanbul and blackouts in Milan. Overall, the results are very promising. However, you can always gain extra precision if you add in some language-specific heuristics. To test the usefulness of our maps as a whole, we looked at both the New York flooding from the Superstorm Sandy and Oklahoma tornado damage maps and compared them to expert damage assessments provided by the US NGA agency. You can see on the left-hand side of these slides is the damage assessment map provided by the experts, and to the right-hand side is the flood or damage map provided by our crisis mapping system. The two maps look pretty similar, and you can see that by varying the quality threshold we can increase or decrease the precision and the F1 score accordingly. Our final evaluation was an end-user survey conducted at 2 European tsunami warning control rooms. The results were very promising, both on the update rate that we could achieve for our crisis maps and on the false positive rates which the end users would find acceptable. This work was performed by the University of Southampton IT Innovation Centre as part of the FP7 TRIDEC project.